Good morning, ladies and gentlemen. My name is Chaoyi from the Bridge Engineering Department of Beijing Jiaotong University. Today, I'm pleased to give a brief introduction about the design and construction of Shanghai Suzhou Nantong Yangtze River Bridge and some related research work our group participated in. My presentation today contains these 6 parts. Firstly, let me introduce the background of this project. From this location map of the bridge on our left hand, we could find this is the city of Shanghai, and this is Nantong, and this is Yangtze River. Okay, Yangtze River is the world's 3rd longest river and China's busiest waterway. And the Shanghai Suzhou Nantong Bridge is located here, near the estuary of the Yangtze River, where the river body is very wide. Near the bridge site, China had already built the Suzhou to Nantong Yangtze River Bridge, and it is the world's first highway cable-stayed bridge more than 1,000 meters. So, we could find it's necessary to build a large-span real-time highway bridge in the estuary region of the Yangtze River Delta. The bridge has a main span of 1,092 meters, and it was once the world's longest dual-purpose cable-stayed bridge for both highway and railway transportation. And the total cost for building this bridge is about $2.15 billion. The total length of this project, including the approaching bridges, is about 11 kilometers, including the 6,989 meters long real-time highway bridge. The main bridge has 432 inclined cables, and the main pylons are 330 meters, and this record of the tallest bridge pylon in the world was just broken last year. And this main span of the bridge is between the pier 28 and 29. Let's remember these 2 pylons. And the bridge construction started in 2014, achieved full span closure in 2019, and opened to traffic in 2020. So China spent 6 years to build this big bridge. And the bridge is also the world's first 4-track railway and 6-lane highway cable-stayed bridge. And the figure on our right hand, we could find the transverse arrangement of this bridge, and the upper layer is for 2-way 6-lane expressway with a design speed of 100 kilometers per hour for highway, and the lower level is a 2-directional 4-track railway that with the design speed of 200 kilometers per hour and 250 kilometers per hour for high-speed railway. Next, I'm glad to introduce some design parameters of this bridge. The water depths of the main piers are 20 meters and 30 meters respectively, because the bridge location is quite close to the estuary of the Yangtze River. And to solve the problem of high depths, the bridge realized an accurate positioning technology for this 15,000 heavy caisson. The caisson is about 15,000, very, very heavy. And considering the requirement for floating, sinking, or installation the upper section in water, a steel structure is used for the lower section, and the concrete section is atop this steel section. And the heights of the steel caisson for the pier 28, 29, these 2 main piers are about 50 meters and 56 meters, divided into 8 and 9 sections. The bottom section is about 8 meters, and the other standard ones are 6 meters. And the height of the concrete caisson atop are 55 and 59 meters respectively, divided into 9 and 10 sections. And the top sections are about, we can find this, 9.7 meters high, and the secant section here is about 14 meters high. Based on the dimensions of this large caisson foundation, the main pylon of this bridge was finally determined as this diamond shape. And the pylon is made of concrete, with considering the good economic efficiency and wind resistance stability. Every pylon is equipped with 33 sets of steel beam, anchor beam here, as shown in this photo. They are steels. They are made of steel, and for this beam, they are 11 meters long and 1.2 meters high, with a weight of 84.4 tons. And the horizontal forces of the dead load in the cable plane will be carried by this steel anchor beam. Due to the large axial forces generated by the inclined cables and the live load induced bending moment, only using these steel truss members are not able to bear the axial forces transmitted from the upper section, and therefore the two-layer, you can find, steel decks should be used to help the truss to carry the loads. As shown in this figure, we could find the lower cord is connected to, this is lower cord, I'm sorry. It's connected to this steel bolt girder with the seam width of the main beam section. This is a bolt girder, but the upper cord is connected to this steel orthotropic plate. In addition, and this Q500 QE steel was firstly used in bridge engineering in China, where we could find this 500 means the yield strength of this steel material. And to test the capacity and the performance, we could find the capacities of tensile, low temperature toughness, fracture resistance, cutting, welding, fatigue resistance, and stabilities were all studied. And this figure shows the development of bridge steel in China from early times when building the Nanjing Yangtze River Bridge to this Shanghai Suzhou Nantong Railway Bridge, and we could find it's the 6th generation of bridge steel in China. Although the three main truss is arranged with 3 cable planes, from this photo we can find there are 3 cable planes. The maximum cable force is still up to 1,300 tons. We know improving the strength of steel wire could reduce the steel amount, facilitate transportation and installation, and minimize the impact of wind vibration onto the cable wires. But traditional cable is difficult to meet this requirement. And so to solve this problem, we could find this ultra-high strength cable with maximum strength over 2,000 megapars was developed to build this bridge. And some parameters just like the tensile strength, elastic modulus, torsion resistance, also the coating uniformity and the coating quality were tested, indicating that the steel wire has a good applicability when adoption in this bridge. To design such a huge bridge, the seismic resistance should always be concerned, and a reasonable structural system is a key to ensuring that the bridge structure has sufficient seismic resistance. The seismic system in this bridge is that the pylon and the girder are not fixed, but the pylon and the pier are fixed together. For the boundary condition, we could find the ordinary spherical supports, the girder vertically, as shown here, just a vertical fixed between the pier and the girder. But for longitudinal direction, something like this, visco dampers are installed between the pylon and the girder to provide the spanning connection, and also for the side and auxiliary piers out of the main span. And these friction pendulum bearings are installed to improve the seismic isolation capacities. And we could find this is the seismic, this plan, for this plan, its seismic resistance effect has been compared with others, with those of other boundary conditions. And we can find the earthquake-induced reaction, internal forces, and displacement. By a comprehensive comparison, finally, China decided to use this plan. And also, modern bridges in the earthquake areas are being built in such a way that they do not collapse during an earthquake. However, it's always not enough for the high-speed railway bridges. To ensure the running safety of high-speed railway, if we want to, there has no derailment atop the bridge, and the structural size must be quite large, but it means not economical. Now, China's approach is similar to that in Japan, and China has established an extensively earthquake monitoring network, which will inform the trains to stop like this when we detect the earthquake motion, and we will inform the high-speed train to stop as soon as possible. At most cases, we allow the trains to derail, as shown in this photo, but we must ensure that the trains do not fall off the beam. In addition to earthquake, another serious problem is wind for long-span cable-stayed bridge, and wind vibration problems are often very prominent, especially for some local vibration, such as onto the cables. Here, I would like to introduce the cable damping technology of this bridge. We could find a pendulum type damper was designed, as shown here. It's fixed onto the cable, and to control the high frequency vortex vibration induced by wind, and using these cylindrical mass blocks to provide internal mass, just like this frame. If there has vibration in this direction, and we could hang a bag, and this inertial mass will limit the vibration of this frame. The principle is similar. Then how to control the low frequency? And at first, we use this oil damper, which is a kind of viscous damper, and it's used to control this low frequency out plane vibration, just like this have a lever to release the energy. Then how to control the low frequency in plane in this direction? Okay, this is a plan of the cable, how to control this direction. The engineers introduced the anti-current damper. From the figure, we could find the damper generates anti-current damping by rotating a high conductivity conductor disc in a permanent magnetic field, and the effect will be amplified by using swing levers to control the in-plane low-frequency vibration of the in-plane cables in this direction. Now we are coming to the construction. Okay, firstly, it's the caisson. The caissons of main pylons were manufactured in sections, and then they were assembled to a hall in the shipyard 10 kilometers upstream of the bridge site. Due to the heavy weight of the steel caisson, it didn't meet the requirement for floating. Yes, because this caisson, we will use barges to ship them onto the location. How to solve this problem, and the engineers decided to seal 12 caisson compartments temporarily and pump air into the compartments by using the air compressors until the caisson floats up. But another problem for the Yangtze River is that the maximum flow velocity at the caisson location reaches 3.50 meters per second, very rapid flow. So, and also if we want to anchor this caisson, the maximum anchoring force of the Palin caisson reaches 9,600 kilonewtons. To solve this problem, and using a large diameter steel like this, you can find this is a steel pails with a diameter of 3.5 meters and 8 concrete gravity anchors weighing to 880 tons. They were placed into the Yangtze River, and these anchor ridges were connected to 16 jets atop the caisson, and the jets were connected with the anchor ridges by using steel wire ropes. And then the multiple directional rapid positioning was done. However, during this work, during the sinking of the caisson, and there occurred a sudden accident due to the rapid and unpredictable flow of the Yangtze River. And it caused a height difference. We can find this. There has a height difference about 13 meters. Okay, quite a large 30 meters difference. So this is a very serious problem when constructing this caisson. So mud section was carried out. This we can find here to set this mud in this area, and also pour the concrete inside the inner wall of the caisson. Then engineers threw the crushed stone onto the lower side to slow down the sporer speed, the sporer effect of the Yangtze River. And after the inland caisson was leveled, and the crushed stone would slide down to the bottom of caisson to support the permanent the supports, to provide the permanent supports. And also these 330 pylons were proposed in 55 sections. Okay, and the pylons were cast using the hydraulic climbing formwork with a standard segment about 6 meters for each section. And to reduce the risk of creaking and complete high altitude pumping for the concrete, the low viscosity concrete was used in the upper section of the pylon, and also creating resistant concrete was used in the lower section. And the concrete of pylon was supplied by the river-based concrete plant, like this. And also for other places, just like pylon base and cross beam, was supplied by simultaneously by both of river-based concrete plant and concrete water board. Now, China has developed the concrete mixing ship for building the similar long span bridges, as shown in this photo. This we could mix the concrete on this boat. Due to the schedule delay, when construction and the pylon atop the Pier 29 and the girder was simultaneously constructed. But if we want to construct them simultaneously, and we must follow these conditions. Firstly, when tensioning the cable, we must ensure the concrete of corresponding pylon segment must achieve 100% of the design strength and have an age of no less than 1 month. And at least for at least 3 standard sections, just like this, 3 standard sections of the pylon must be constructed above the inclined cables when we want to follow this simultaneous construction. And the steel truss was erected in a very large section. So when erecting a section of the girder, it's necessary to complete the installation of tensioning of at least 12 inclined cables for each time, for 2 levels, as shown here, the 2 levels, and in transverse direction, and 3 cable plans. Okay, this is a traditional steel beam construction, and we know normally the steel beams were manufactured and assembled using single truss member, less than 100 tons. But for this bridge, we can find when building the girder at pier top, a single truss section, just like this, or 1/2 truss section was manufactured in the plant and shipped by the barges, and the sectional weights about 1,000 to 1,200 tons, and we use this 1,800 tons floating cranes to lift the section onto the bracket to support the erected girder. But for the other heavier sections with a maximum weight more than 1,700 tons, China developed 1,800 erection crane like this, okay, to erect the other heavier sections. Also, to achieve the closure of the mid-span as soon as possible and reduce the risk of large cantilever construction, the original design of closure scheme set span first and then mid-span was adjusted. We follow these screens and we could find. And also, because the main girder has a high stiffness, because it will be used for high-speed railway. So it's quite difficult to adjust the closure joint at final stage. So we can find the following closing sequence is adopted. Okay, from the lower chord of mid-truss, set truss, and I don't know, follow this one to achieve the final closure. And then I'm pleased to introduce some research work of our group in this bridge. In 2018, we went to the construction site, measured the wind fields at the pillion top, highway deck, and railway deck, and obtained the fitting parameters for the wind power spectrum. Okay, and the wind velocity histories of this long-span cable-stayed bridge could be used in bridge aerodynamic analysis. We could find these photos were taken during our set test. We used the ultrasonic anemometers and traditional mechanical anemometers to measure the wind speed. By using the measured wind speed, we evaluated the running safety of the train. Okay, atop the bridge under the high wind, we want to check if there has any problem for the running safety of the train under high wind, and comparing with the traditional simulation, our bridge model was established considering the geometric nonlinear factors, just like the sag effect, beam column effect, and the large displacement effect. And the results show that ignoring the influence of nonlinearities will lead to inaccurate response analysis and unsafe evaluation. Another work I would like to introduce is related to the riding comfort of the train and the management of the track deformation for the long-span railway bridge. Here we could find the static smoothness of ballast, like this, ballast and ballastless tracks on the main lines of high-speed railway and the intercity railway. This slide shows the ballast and ballast lines here. And from these tables, we could find in the new code, and this 60-meter mid-chord offset is supplemented. We could find from this slide, it shows how to calculate this mid-chord offset, okay, within 60 meters. This is 60 meters. And yes, I must emphasize that the newly added mid-chord offset refers to the static longitudinal irregularity on the newly built high-speed railway bridge spanning from 200 meters to 1,100 meters. And the values have been processed after 200-meter high-pass filtering. Okay. And why we must use this value? Because according to the practice and the scientific research in many countries, and it has been proved that this value directly reflects the car body acceleration. So if we want to control the riding comfort of the high-speed train, we need to control this value. And also through set test and simulation of this bridge, another 1,000 meters suspension bridge, Wufengshan Yangtze River Bridge, and some long-span railway arch bridges in China. It shows that the wavelength component, about 200 meters, has a relatively significant influence on the 60-meter mid-pole offside, but it has a relatively small influence on the car acceleration. So to effectively reflect the car body acceleration and facilitate the track management, it's suggested to have a 200 meters high-pass filtering for static irregularity. It means that we could keep the component with the wavelength more than 200 meters. And this is the correlation between this 60-meter mid-pole offside and the car body acceleration under 250, 350 kilometers per hour. And these formulas could be fitted by a set test. Okay. And then if we know the allowable car body acceleration, A, and we could obtain the limitation of the 60-meter mid-pole offside at different running speed. Okay, so this is another important scientific research results obtained from this bridge. Finally, we come to the perspective after the construction of the Shanghai Suzhou Nantong River Bridge, and China built Chaoyi Yangtze River Bridge last year, and the highway part, the highway transportation was opened to traffic last year, and we could find this bridge has a main span of 1,176 meters. This is a transverse arrangement for the transportation. We can find the upper layer for expressway. This is the upper layer. The lower layer is arranged for the intercity railway and ordinary highway. This is a traditional symmetric transverse arrangement shown in this shown here, in which we can find the right side ordinary highway approaching bridge must pass through this railway approaching bridge to meet with the left side highway approaching. So thereby it will increase the land occupation. To solve this problem, finally, and China decided to use this symmetric arrangement. We could find and the left part for highway and the right part for railway. But this arrangement will lead to another problem because of the huge difference in load on both sides of the bridge. The railway side weighs almost 30,000 tons, while the highway side weighs only less than 10,000 tons. So with a weight difference about 3 times. To save this problem, and we could find, and the solution is to enhance the tension of the railway side stay cables, and then the overweight side will be lifted up to balance the effective load on both sides. Also, at the same time, the manufacturing shape of each component was accurately calculated to offset the lateral deformation caused by the uneven tension forces. And also, this is the external press-stressed tendons. They were installed to adjust the offset of the pylon caused by these symmetric loads. And also to reduce the caisson weight and the cap size, a stamped caisson was firstly adopted in China, like as shown here. This is a stamped caisson, and there have two sections. The bottom section with 5 layers is about 43 meters. Okay, at least 43 meters, and it was manufactured in the plant and assembled in the land dock before being floated to the construction site. And the top section with 3 layers, it was produced in blocks like this, many blocks, and the blocks were produced in the plant, transported by barges and assembled on the construction site. And also from the construction of Shanghai, Suzhou, Nantong Yangtze River Bridge, the technologies like sonar and ultrasound and underwater robots, lots of underwater technologies were tested, as shown on our left hand. But to build this Shanghai Yangtze River Bridge, we developed an intelligent tracked twisting and suction robot. Okay, and compared with the traditional robot, and its suction capacity, okay, has increased by almost 5 times. Okay, from this we can detect and observe the foundation condition at any time. Also, considering the column, considering the stress on the upper pylon, okay, for this part, the pressure exceeds 50% due to the vertical axial force, and we must also consider the difficulty of controlling the concrete creating. So, and China adopted steel bolts. Actually, this is a steel box. Oh, sorry, this is a steel box and the core concrete. This is a composite anchorage system in this upper section of the pylon, and the core concrete is not only the anchoring structure for the interland cables. As shown here, we can find the interland cables. This is interland cables anchored at this core concrete, but this part also takes part in the pylon stressing when being compressed, and this design could greatly save the construction cost. And normally, for a double pylon cable stayed bridges, it usually adopts a semi-floating system when the main girder is supported vertically by the bearing, but in longitudinal direction there is no clear constraint. Okay, so that when it's floated, it could move freely in longitudinal direction. But if we follow this design, we could imagine that the displacement at the girder end should be quite large, making it difficult to design, produce, and maintain this railway expansion adjuster or even the highway expansion joints at the girder end. Another kind of scheme is that we could fix the longitudinal boundary conditions. And if we follow this scheme, the longitudinal constraint will limit the released temperature deformation of the steel girder when system temperature changes, resulting in a significant additional temperature falls. So to solve the problem of this long-span cable stayed bridge, and a temperature adaptive longitudinal constraint system was proposed. We can find under the temperature fluctuations, the semi-floating cable stayed bridge with symmetrical arrangement has a fixed point A at the midspan. Therefore, if we fix the longitudinal displacement at point A, it will not restrict the deformation release during the rise and fall, temperature rise and fall. And then if point A is connected to points B and C at the pylons, it not only achieves longitudinal constraint between the pylon and the girder, but also does not affect the release of temperature stresses. And finally, and the CFRP strands, which are not sensitive to the temperature changes, are used as the connecting bars between point A and point B, C. Okay. Finally, and we want to talk about some other perspective. You know, China's infrastructure construction has slowed down in recent years, and we are increasingly pay more attention onto the full life cycle of bridges, including the plan, design, construction, and operation. And we want to introduce some AI technologies into the various stages design and management. And also, because of the aging population in China, many institutes and universities are developing the automated concrete plant. 2 years ago, I went to a plant. The boss told me that there had only 20 workers in his plant, and all of them were not measuring with civil engineering, but mechanical engineering, and they were responsible for repairing the robot arm, and also something like this, some robots like this, and also engineers said to me they had to employ 25 workers and spend half a day to carry out this steel bar bending. So that's why there has an urgent requirement for developing the robots in future, and also some lightweight monitoring system and inspection robot, okay, have been developed and are promoting in heavy bridges and in some railway bridges. And finally, this is the maybe modern bridge health monitoring system integrating the satellite and the UAV and underwater robot maybe in future, and we could just use a smartphone and stay at home to check there is any disease of our bridge. And this slide shows the references of the presentation. Okay. Finally, thank you so much for all of you. I would like to share my sincere hope for the coming Lunar New Year. Thank you. Okay, dear ladies and gentlemen.
Okay, thank you, Professor Sa.
Thank you.
I think that some experts will have some question for you. Okay, any question from the delegation? Về câu hỏi nào? Có thể lên. Anh nghe chuyện này vậy. Như một bạn thầy cấm mic cái, lấy nhơi cấm mic của anh ta. Có tiếng Anh nhé.
Thank you very much, Professor. It's an excellent lecture. I have a question about the design and the construction of basin. Why you to divide the two sections, including the concrete and steel for the facing? For the first case study, another case study you use only the steel for the facing.
Okay. Okay, thank you, sir. And it's not so clear at my side, and I just would like to explain that. Sorry, I need to share my screen.
Yeah.
Okay, and your question is about why we need to produce the Kaizen within many sections.
About the Kaizen construction and design.
Yes. And why we divide the case into many sections.
Yeah.
Yeah, because normally it's very difficult to to produce a whole Kaizen, because the Kaizen is very, very big. For this Shanghai, Suzhou, Nantong Yangtze River Bridge, the area of Kaizen is almost equivalent to 12 basketball pounds. Okay, yeah. Very big. And the height is more than 100 meters. So it's very difficult to manufacture a whole section. And so if we want to float, or maybe float it and ship it from the dock from the shipyard to the location, the bridge location, we must make it as light as possible. That's why I think I can share this one. Oh, this slide,
Okay.
and that's why. Okay.
Yeah. Okay. Very clear. Yeah.
Yeah. Oh, you can find this is sorry. Oh. Okay, we could find. This is the steel section,
Yeah.
and this height is very huge. So, and if we want to have an accurate manufacture in the plant, it's also quite feasible to make it or produce it in sections and then weld them together. Okay,
Yeah.
and this part is the concrete caisson. Okay.
Yeah.
Yes, and this concrete caisson will be completed when the bottom part was shipped to the location site. So we could find this part was constructed at the location. Okay.
Okay. Well, thank you, Professor Sa.
Thank you.
Tại sao cái công chứng chỉ là cái quyền hai đốt, bạn bên dưới là bằng thép, chứ có bên trên thì dùng cái con. Dù cái mong chỉ này.
I would like to explain that why we must use the caisson foundation is because. Sorry. Oh, sorry. I would like to explain why we use this caisson foundation because this bridge is close to the estuary, so it's very difficult to build the pale foundation. Okay.
By solution.
Yeah. Very huge steps. Yeah.
Okay, very clear. One more question, Professor Nhâm.
Okay,
Okay, we're going to translate into Vietnamese. A moment, right?
Đa số là đọc Hà Nội. Với đọc Hà Nội thì hiện tại ta đã được đọc nên đối với các cái tải trọng lớn thì có thể đọc Hà Nội tư tác đã đủ. Ngoài ra trong cái dự án này thì giáo sư có giải thích là gần cửa sông nên là có công
cổ vật lớn thế.
Mời thầy Nhâm ạ.
chia đôi một
Sorry.
tức là đối với thép thì sẽ hơn cái chuyện người ta cũng phải dùng các tàu chuyển nhưng mà cái chiều dài của cái chiều này ở trong cái đoạn này là khoảng hơn 100 mét, cũng là sâu hơn 100 mét. Lượng rất lớn như vậy không thể công trong nhà máy mà lấy kéo được, đấy là lý do liên quan đến các bên trên của quốc phòng về sông cũng rất là
cái ý của thầy thực ra cái chương trình dạng này 18 cái mong tìm từ 8 mét và đi khoảng 6 mét thì là trước chân rất là lớn, không thể áp đặt theo công nghệ là không thể làm được bằng cái nào đều ở những bên dưới của nó phải như là không cho bên hầu đó là trên cái thứ tiếp nhìn dần và khi tiếp đất rồi thì lúc đó là được như không. Thế và ở cầu Thăng Long cũng thế, và ở đây trong trường ở cái cầu này cái sẽ còn nó đã cháy thì lại không ý nghĩa gì thì hơi ép. Thì như vậy là để tạo ra cái độ nổi của nó mình vẫn để bước ra khỏi để có thể là tiếp vào đất đá ở bên dưới thậm chí để lại còn không có như vậy là cái gần đến nhất đi tìm tới nhất là nhiều nhất mà không nhất thì với cả ba dạng thì trên đảo cái bài cái đề giờ thứ nhất. Còn bây giờ tôi quay trở lại, tôi xin thầy Anh giúp. Tôi rất là cảm ơn cái bài giới thiệu rất là hay về trường hợp và cái công của cái kết cấu, và đặc biệt là cái chỗ tôi đã đi số chung cặp đường sắt thường, tức là thiết cắt tốc cao, tức là nó khoảng đến 200 km đường sắt thường phía bên trái, thế rồi là đường sắt tốc độ cao, và bên trên nữa thì lại là ô và đường bộ. Vậy thì trong trường như thế này, với kết cấu như thế thì cái tiêu chuẩn nào là tiêu chuẩn chính thống để khống chế? Bởi vì như vậy, nếu như là theo tiêu chuẩn đường bộ và tiêu chuẩn đường sắt thông thường không yêu cầu cao như thế, nhưng bởi vì đây tất cả cái thành phố là đường sắt tốc cao, vậy thì trong trường này thì là sự tiếp cận như thế nào thì là hợp lý. Và đây trường chúng tôi thì trong tuần trước tuần chúng tôi nhưng mà hôm nay được nghe chính khi báo cáo về cái cầu mà chúng tôi đã rất là quan tâm đến này, thì xin có cho biết thêm về vấn đề này.
Professor Nhiệm have a question that this bridge used for the railways, high-speed train, and also the highway. So which kind of the standard you apply in the design process?
Yes, we use the railway design code. Okay, like this, comparing with the railway, we think the highway load is quite low, especially if we compare the bridge like this Shanghai yangtze River Bridge, which was just constructed last year. We could find almost 3 times. Okay, for this side, for the railway side, and the load is almost 3 times than the highway side. And another important thing, in addition to the load carrying capacity, is about the deformation. Because for highway and for automobiles, their riding comfort or maybe the riding safety is not so problem, not so serious. But for high-speed railway or even railway, we must strictly control the deformation. So that's why for the highway design company, maybe they don't have so much experience in solve this problem to control the deformation and to considering both of the deformation of bridge and the tracks. But for railway design companies and similar institutes, and they have rich experience to deal with this problem. Just like this, I have just listed here about the smoothness of the track. Yes, normally because for design a highway bridge, and the deformation is not so strictly controlled. Even in our design code, we stipulate that the midspan must realize a set value, must be lower than an allowable value, but it's not so strict. But for railway bridge, in addition to midspan, we need to consider the rotational angle at the beam end, and for some other deformations to make sure there has no problem, not only for riding safety on the trains, but also the riding comfort for the passengers. Okay, that's why in China, most of, I think all of the real calm highway bridges were designed by railway departments. Okay, and we follow the railway design code and standard. Okay.
Okay, thank you.
Okay.
Là thầy tức là như vậy là hỏi cơ bản chung như vậy là họ bảo là về mặt tải trọng đường bộ thì chắc là nó sẽ ít hơn rất là nhiều so với đường sắt, cho nên là tất cả là đều quy chiếu về hệ đường sắt là phần lớn, vì tất cả những chỉ số cho phép về mặt độ vòng này kia là theo đường sắt
thường là đường sắt cao.
Vâng.
Đường sắt nào?
This is the highway speed, right? By on the technical standard of highway bridge design.
Yes, this I need to. Yes, this is a final design, and at first we want to have a symmetric Okay, like this. This is a symmetric. In the past, we follow this arrangement, and this highway, this is expressway with a design speed more than 100 kilometers per hour, and this is intercity or high-speed railway. But we have a problem. You could imagine that we must meet this highway lengths together. So the general solution is to let this side highway to pass through below the railway. So it will waste much land resources. So that's why we follow another design. Okay, sorry. This is the final design, and we could find the highway are together and the railway are together. But the problem is that the eccentric loads. Okay.
Vậy là nó cũng trải qua nhiều cái mặt cắt ngang khác nhau để nó mới lựa chọn được cái loại giống như hôm nọ cầu mình đi là như vậy là đang thường một bên chưa làm đúng không? Hôm nọ là một bên họ làm với cái đường sắt tốc độ cao, hôm nọ mình đi nó chạy đấy. Mới chỉ có một bên, có người nào đó hỏi tại sao một bên kia không chưa thấy có gì.
Yes, normally, when we design highway bridge, the stiffness control is not always our primary concern. But when we design a railway bridge, both of strength and deformation control should be concerned.
Yeah.
Yes. Okay.
One more question.
Chắc là thầy của em là nhờ giáo sư đã chia sẻ về yêu cầu đặc điểm gì về cấp phối bê tông, về thành phần hạt, hình dáng hạt.
In China, do you have any requirement on the concrete, the component of the concrete structure? Maybe about the cost material, stone. Do you have any requirement about the stone or sand or cement?
Yes, we have our requirement about the size, both. But for railway and highway, they are a little bit different because the railway and highway belong to different ministries, and we have our special requirement for the sands of aggregate and also sand, lots of things. Okay. But I'm sorry that my major is not about material, so I only know a little about this concrete.
Có quy định là vì là đường sắt và đường bộ hai bộ khác nhau, nhưng có quy định có hai bộ tiêu chuẩn khác nhau. Bạn này thì về không phải là về vật liệu cho nên ông cũng nhớ được là cái chân có. Chắc là thế thôi nhỉ. Ok là vậy thôi. Ok, thank you, Professor.
Thank you.